Hello, in this video, we'll continue talking about Bayes statistics and focus on Bayes theorem. And in this video, we will focus on the influence of sample size on the posterior. So this is the Bayes rule, and this is the posterior probability from we get the result and update, and we get the conditional probability of C when R is given. And this probability PC is the prior. So before we get the information for the R, we only know this prior probability. Then probably this conditional probability of R given C is called the likelihood. So likelihood means for which value of the parameter C and what's the probability of the R under this parameter value. And the denominator is called evidence or the total probability, which equals the odd likelihood multiplied with odd corresponding value for probability C. So here we use P asterisk for different values of C, and here prior is for a given. So for example, now we will test with the case for flipping a coin with head and tail results. Say that we are interested in the candidate values of theta, which is the constant probability for head in each trial. And we will think available value for this theta like the C in Bayes formula, right? So we think there are 1,000 values or 1,001 available values for theta, from 0.0 to 1 and with 0.001 in the gap. So there are 1,000 plus 1 values available for theta, right? So for each one value, we have a Bayes formula to get the posterior, right? So now we will plot figure based on prior information, likelihood information, and posterior. And we focus trying two experiments. In two experiments, we start with the similar or very close triangular prior for these 1,000 candidate values for theta. Then the likelihood from the data side. So we know the likelihood is the data, right? So this is the data because we will calculate the conditional probability of the data occur given different values of these parameter, right? So this is the likelihood, or say that this is the data. So we will plot prior and data, or say the likelihood, and we'll get the posterior for this 1,000 theta value. And for the data, there are two different scenarios. And the first scenario is small data. So we have 4 flips in total, but only get 1 head. And second scenario is a relatively large data set with 40 flips, and we get 10 heads. Why we use this number? Because we want to use the same proportion of heads. So we have the same proportion but different sample size. So this is what we want to get the result for the influence of sample size on the posterior. So after calculation for 1,001 times for the posterior, we get this posterior, and this is the prior, which has triangular with the mode here 0.5 and 0.5 is the highest density, and this is the likelihood. So the likelihood is the data because because there are only 1 of 4 head. So you can see the mode is 0.25. What this means? This means this value can get this result. Other value can also get this result. But the probability of this value will get the highest probability of this result, right? So the mode same as the frequency, then this will get the highest probability for this parameter. And same as this one, but you can see here, because the data relatively large, so this likelihood will be has high mode, not so flat one, relatively it peaked. And so from almost the same prior, but we have different sample size, can see the posterior will be different. And in the first case, the posterior is quite flat and the mode is close to prior. Prior mode is 0.5 here, and actually here is 0.4. And this is 0.25. So the mode of posterior is between the prior and likelihood mode. But in a small data sample scenario, the mode for the posterior relatively close to the prior. And in the large data sample scenario, the posterior mode is very close to the likelihood mode. So here 0.25 and here almost 0.28 like this. And far away from the prior mode. So this is what we have seen in the figure. So the left, the mode peak of the posterior is at 0.4, which is close to the mode of the prior, then the mode of the likelihood function. And for the large sample size on the right, the mode of the posterior is 0.268, which is close to the mode of the likelihood function. So we can get some conclusion. The mode of the posterior is between the mode of the prior and the mode of the likelihood. But the posterior of mode is close to the likelihood for the large sample size. And the width of the posterior highest density interval, HDI, is smaller for the larger sample size. So what is highest density interval? If we look at this posterior, so this range is the highest density interval. So in the Bayesian statistics, compared with the traditional frequentist statistics, which focus on the confidence interval from the hypothesis testing, but the Bayesian statistics not use this kind of confidence interval. Bayesian statistics use highest density interval. Highest density interval HDI, which means for this range, all the probability density will higher than the density out of this range. And same as this one, for example, this range from 0.16 to 0.4, this range, the probability density higher than other probability density values out of this range. So this is the highest density interval from 0.151 to 0.412. So you can see the large sample size, the HDI is narrow, but for the small sample size, HDI is wide. And narrow means high accuracy, high precision, right? Because if the range is very wide, just the same as this one prior, so we get nothing new, right? But highest density, narrower, the precision is higher, is the better, right? So in general, the more data we have, the more precise is the estimate of the parameters in the model. So we get very precision of the parameter on small range. So large sample size will yield a greater precision or certainty of estimation in Bayes statistics. And we also have a website for Python and R training, and both having general programming and statistics tutorials. Thanks for watching.